This is a necklace polynomial, and these are its roots. They look like a necklace. Of course, 0 is also a root, but we can label that as the neck. This is the 21st necklace polynomial, but the same happens with the 20th or 19th or any necklace polynomial. We always get a root necklace and a 0 neck. Some are evenly spaced. Very nice. The 35th contains multiple of these even Stevens. And then there's the 55th with its incomplete Pete. In this video, we'll find out why these necklace shapes appear, and then dive a little deeper to learn about the regular and not quite regular patterns. This is the 8th necklace polynomial. It tells us the number of 8 bead necklaces if we use X colors and no repetitions. So if we input 2 colors, we get 30 necklaces. Here they are. If we try to add a new necklace, it will either be a repetition of something we already have, a rotated repetition, or it will have self-repetition. This one is made of 2 identical copies. We can only make 30 necklaces without repeating. And notice, these two make a flipped repetition, but that's okay. In mathematics, you can't flip a necklace upside down because that would make it a bracelet. And this video isn't about bracelet polynomials, it's about the necklace polynomials. Speaking of which, where does this expression come from? Remember, it's the number of 8 bead necklaces using X colors. So, there are X options for the color of the first bead, and then there are X options for the color of the second bead, X options for the color of the 5th bead. Thank you for watching, for a total of X to the 8th necklaces. But remember, we're counting with no repetitions. This X to the 8th includes self-repetitions. Some repeat a 4-bead segment, some a 2-bead segment, and some just 1 bead over and over. But in each case, we have the left and right half being identical. So how many ways can this happen? Each side has 4 beads, so there are X to the 4th self-repetitions. Let's subtract those away. So now we have no self-repetitions. But this still includes rotated repetitions. Each necklace has 7 rotated clones. So we need to divide by 8 to get rid of them. And there's the polynomial. We see something similar in the other necklace polynomials. There's this front fraction to account for rotations, and then we have small powers that divide the largest to get rid of self-repetition. And this means that we always have some largest power that dominates the other powers. So a big number can't be a root. If we input a big number like 100, this can't equal 0. The small powers can't cancel out that 100 to the 55th. And this is even a problem if we just input 2. That highest power is too big. So the magnitude of the roots must be close to 1. Or in other words, the roots must be near the unit circle. And this is why we have the necklace shape. Now, what about the even Stevens? Why is the 17th root necklace so nice? There are X to the 17th total 17 bead necklaces, but we need to remove repetitions. 17 is prime, so the only self-repetition is 17 copies of the same color. And there are X colors to choose from, so we just subtract X to get necklaces without self-repetition. But then we still have rotated repetitions, so we divide by 17 to get our final polynomial. Let's factor this. On the left, the root is 0. This gives us the next 0. And on the right, the roots are the 16th roots of 1, which are nice. They form a 16-pointed even Steven, or a 16 Steven for short. The same applies for any prime number p. The polynomial is 1 over p times x to the p minus x, which factors to give us a next 0 and a p minus 1 Steven. And these primes carry forward. The 55th necklace polynomial includes a 5 minus 1 Stephen and an 11 minus 1 Stephen. But as you may recall, it also includes an incomplete Pete. This one is a 12 Pete. Where does it come from? The 11 minus 1, or 10 Stephen, is the roots of x to the 10th minus 1. So we can factor that out, as well as the next 0, giving us this expression on the right. And we notice the powers are evenly spaced. There's a gap of 10, 10, 10, 10, 4, and it's negative. To get the full pattern, this should be x to the negative 6 instead. So we'd like to make this replacement, and we can if negative 1 equals x to the negative 6, or equivalently, x to the 6 equals negative 1. The sixth roots of negative 1 allow for this replacement, and it turns out they're roots of this expression. If we take this as r, then r to the 6th is negative 1, and plugging r into this expression gives us 6 evenly spaced terms, which add to 0. And this explains the incomplete Pete. Out of all the 12th roots of 1, half are 6th roots of negative 1, so the replacement will work. But the other half are 6th roots of 1, so we can't make the replacement, and this expression stays lopsided at the end. They're not roots. So the 55th necklace polynomial has this 12 Pete that's half full, or half empty, depending on your perspective. Although we actually also get these 2 points, since they're part of the other Stephens. So now it's mostly full, or still pretty empty, again depending on your perspective. In general, for any primes p and q, the roots of the pqth necklace polynomial will contain a p minus 1 even Stephen, a q minus 1 even Stephen, and a 2 times p minus q incomplete Pete, if this divides p plus 1 times q minus 1. To see why, we can factor this just like we did before, and we get this expression, which has p plus 1 terms, and the powers are separated by q minus 1, for a total span of p plus 1 times q minus 1. But we'll also need to replace negative 1 with x to the p minus q. This will work for half of the 2p minus qth roots of 1, as long as 2p minus q divides that span, because the terms need to make a full loop. So there you go. For another concrete example, the 133rd necklace has a 6 Stephen, an 18 Stephen, and then a 24 Pete. And we start with half of the points, but then fill in these ones from the Stephens. For a weird example, the 91st necklace polynomial has a 6 Stephen, a 12 Stephen, and then a 12 Pete. But of course this gets completely filled since we already have a 12 Stephen. We only really need the one in the middle to describe everything. So in conclusion, the roots of the necklace polynomials look like a necklace and sometimes have interesting patterns. If you enjoyed this video, you can support the channel. I'm now on Ko-fi. You could become a member or just buy me a one-time coffee to help fuel the next video. Thanks to Balak, my first supporter, who found the page before I even announced it. And of course, thank you for watching to the end. I'll see you in the next video.